Welcome to Heat Transfer video lectures. In this video, we will look into Unit 2. The title of Unit 2 is Fins. And these are the contents of Unit 2. Definition and types of fins. Fins of uniform cross-section. Governing equation. Temperature distribution and heat dissipation rate for long fin, short fin with insulated tip and convection of condition. Then convective of condition. So these are the contents of your fins. So in addition to that, efficiency and effectiveness of fins will be discussed. Then coming to the introductory part of fins. First of all, let us understand what is fin. The heat conducted through solids, walls, or boundaries has to be continuously dissipated to the surroundings or environment to maintain the system in a steady state condition. If you look into the many engineering applications, large quantities of heat have to be dissipated from small areas. Heat transfer by convection between a surface and the fluid surroundings. It can be increased by attaching to the surface thin strip of metal called fin. So the fins increases the effective area of the surface, thereby increasing the heat transfer by convection. The fins also referred as extended surfaces. Fins are manufactured in different geometries depending upon the practical application. So here the finned surface are more commonly used in practice to increase the rate of heat transfer as we know. The rate of heat transfer from a surface at a temperature Ts to the surrounding medium at T is given by Newton's law of cooling. Q is equal to H As Ts minus T infinity. See, there are two ways to increase the rate of heat transfer. To increase the convective heat transfer coefficient H or to increase the surface area. So increasing H may require the installation of pump, fan. That means some external agency we require in order to improve the convective heat transfer coefficient. The alternative way is to increase the surface area by attaching the extending surfaces, which are called pins. So, which are made up of highly conductive materials such as aluminium. And these particular fins are manufactured by extruding, welding, wrapping a thin sheet of metal on a surface. The fins enhances the heat transfer from a surface by exposing large surface area to the convection and radiation. So these are the various applications where we can able to see the fins. Engine cylinder, the radiator, transformer, condenser coil we can able to see. The fins are attached. Compressor cylinder if you observe, and radiators. So yeah, in all these particular applications can able to see the fins in order to enhance the heat dissipation rate. Then here, these particular fins are manufactured in different geometries depending upon the practical application, some of which are shown here. So here, longitudinal fins we can see the ribs attached along the length of the tube are called longitudinal fins. Concentric annular disc around the tube, so which are termed as circumferential fins. So pin fins are spines. Those are rods which are protruding from the surface. So these particular fins may be of a uniform cross section or variable cross section. So they have many different practical applications like cooling of electronic components, cooling of motorcycle engines, compressors, electric motors, transformers, refrigerators, high efficiency boilers, superheater tubes, so on. So many applications we have. Then coming to the fin analysis, for proper design of fins, the knowledge of temperature distribution and rate of heat transfer along the fin is necessary. So while making analysis, heat flow analysis through the fin, these particular assumptions we have to consider. First one is steady state heat conduction, no heat generation within fin, uniform heat transfer coefficient, Over the entire surface, material is isotropic, heat conduction is one-dimensional, and negligible radiation. Then rectangular plate fin of uniform cross section we have taken for our analysis. Okay. So here the the figure shows a thin rectangular fin of uniform cross section. So the principal heat conduction along the x-axis, whereas the convection loss takes place from the upper and under the surfaces of the fin. Assuming the base temperature as T naught of the fin to be uniform and thermal conditions at the tip of the fin to be non-variant in z direction, and a constant thermal conductivity of the fin material with its thickness to be very small compared to its length, steady state conditions are prevailing. So here, one-dimensional heat conduction will exist and the temperature distribution will be the function of x coordinate, the properties of the fin and the convective heat transfer coefficient. So to determine the governing differential equation for the fin shown in the figure, consider the heat flow to and from an elemental cross-section ds thickness and distance x from the base. So we can write a heat balance for the element as Qx is equal to Qx plus delta x plus Q convection. So where Q convection can be written as H A delta T, where A is P into dx, we can write T minus T infinity. Then dividing with the delta x, so the equation becomes like this. Then taking the limit as delta x tends to 0, we can get dq by dx plus hpt minus t infinity is equal to 0. So from Fourier law of heat conduction, we have q conduction is equal to minus ka dt by dx. So substituting the same in the previous expression, we will get the differential equation for the fin. Then in general case, the cross-sectional area and the perimeter of the fin vary with x, and which makes the differential equation a bit difficult to solve. So in the special case of a constant cross-section and constant thermal conductivity, so the differential equation reduces to d square theta by dx square minus m square theta is equal to 0, where m square is equal to hp by kc. Okay, and theta is equal to T minus T infinity is the temperature excess. At the fin base, we have TB is equal to TB minus T infinity. So equation the 7 is a linear homogeneous second order differential equation with constant coefficients. Okay. Now, a fundamental theory of differential equation states that such an equation has two linearly independent solution functions and its general solution is linear combination of those two solution functions. Okay, so the differential equation, what it reveals that subtracting a constant multiple of solution function from its second derivative yields to 0. So we can say that the function and its second derivative must be constant multiples of each other. So the only functions those derivatives are constant multiples of the function themselves are exponential functions. Okay. So the solution functions of the differential equation above are exponential functions e to the power minus mx or e to the power mx. So therefore the general solution of the differential equation, that is d square theta by dx square minus m square theta is equal to 0 is theta of x is equal to c1 e to the power minus mx plus c2 e to the power mx, where c1 c2 are arbitrary constants and whose values are to be determined from the boundary conditions at the base and at the tip of the fin. And these are the boundary conditions. Okay, so these are the boundary conditions at the fin base and fin tip. So here the temperature of the plate to which the fins are attached is normally known in advance. Therefore, the fin base we have a specified temperature boundary conditions, so which can be expressed as the boundary condition at the fin base theta of naught is equal to theta b is equal to tb minus t infinity. So the other boundary conditions depends upon the physical situation. There are several cases may be considered. Okay, the case one is the fin is very long and the temperature at the end of the fin is essentially that of the surrounding fluid. Case 2 is at the end of the fin is insulated so that dt by dx is equal to 0 at x is equal to L. The fin of finite length and loses heat by the convective from its end, convective of conditions. Okay, so these are the different cases we are considering. Okay, next case 1, infinitely long fin. So for infinitely long fin, so what is the temperature distribution relation and efficiency, I mean effectiveness, okay, and heat flow. So that expressions we will look into. So this is the general solution of the equation, then which may be written as the general solution for the differential equation may be written as c1 e to the power mx plus c2 e to the power minus mx is equal to 0. Then for case 1, these are the boundary conditions. Theta is equal to theta b at x is equal to 0, theta is equal to 0 at x is equal to infinity, let theta is equal to t minus t infinity. Applying boundary condition 1, we can get c1 plus c2 is equal to theta naught. Applying second boundary condition, we will get this expression. So as c1 e to the power m infinity tends to infinity as x gets larger. Okay. In such case, the c2 is equal to 0, c1 is equal to theta. And substituting the c1, c2 values in the equation 1, we will get theta by theta b is equal to t minus t infinity divided by tb minus t infinity is equal to e to the power minus mx, where m square is equal to hb by kac. So this is the heat transfer from the entire fin under steady state conditions. Q long fin is equal to minus Ka dt by dx. Okay, then this can be written as square root of Hp Ka of Tb minus T infinity. So similar way, case 2, negligible heat loss from the tip fin, which is nothing but the insulated fin tip. So Q fin tip is equal to 0. Then coming to the boundary conditions at the fin tip, d theta by dx at x is equal to L is equal to 0. So this is the condition at fin base, okay, which can be expressed as theta of 0 is equal to theta b is equal to tb minus t infinity. Then applying these particular two boundary conditions to the general solution, as already we have seen the general solution, then after some manipulations, this relation we are getting t of x minus t infinity divided by tb minus t infinity is equal to cos hm l minus x divided by cos h ml. Then the rate of heat transfer from the fin for that particular case 2, okay. So Q insulated tip is equal to minus KAC dt by dx at x is equal to 0, then which can be written as square root of HP Kc of Tb minus T infinity tan H ml. Then this is the convective of conditions, the convection from fin tip. Okay. So here the fin tips in practice are exposed to the surroundings. Thus the proper boundary conditions for the fin tip is convection, that also includes the effects of radiation. So this particular fin equation can be solved in this case using the convection at the tip and as a secondary boundary condition, but the analysis becomes more involved and it results lengthy expressions for the temperature distribution and heat transfer. So in general, the fin tip area is very small. Okay. So when compared to the total fin surface area, so the complexities involved can be hardly justify the improvement in accuracy. So the practical way of accounting for heat loss from the tip is to be replaced by the fin length L in the relation of the insulated tip. So in case the corrected length we are considering, corrected length can be defined as L plus AC. AC is cross-sectional area divided by perimeter of the tip. Okay, so that indicates that the fin area determined here, then multiplying this particular relation above by the perimeter gives A corrected is equal to A fin lateral plus A tip. Okay, so this particular expression indicates that the fin area determined using the corrected length is equivalent to the sum of the lateral fin area plus the fin tip area. Okay, so this is the case for the rectangular as well as cylindrical fin, the corrected length expressions. This must be remembered, L plus d by 2 and this is L plus d by 4. Then coming to the fin efficiency. Okay. Now, fin efficiency can be defined as it is a ratio of actual heat transfer rate from the fin to the ideal heat transfer from the fin if entire fin were at the base. Okay. So, for which, if you refer to the figure 7, so figure 7A is surface without fin, and figure B is surface with fin. Okay. Then this mathematically expressed as Q eta suffix fin is equal to Q fin divided by Q fin max. So here the efficiency of the fin is nothing but, one more time I'm repeating, ratio of actual heat transferred by the fin to the maximum heat transferable by fin if entire fin area were at base temperature. Okay, so the maximum heat transfer would occur if the temperature of the extended surface was equal to the base temperature T naught at all points. Okay, so here the expression for long fin and insulated fin, as well as here the q fin is equal to eta fin into q fin max. Okay, reference to this. So for long fin efficiency and for insulated tip we can able to write. For long fin 1 by ml, for insulated tip tan h ml by ml. Then fin effectiveness. So the performance of fins we can able to express in terms of fin effectiveness. Fin effectiveness is the ratio of heat transfer rate from the fin of base at area AB, heat transfer rate from the surface of area AB. Okay. So here this you can see in the figure 8. Okay. So this is the surface without fin and this is the surface with fin. Okay. By providing the fin to the surface, so what is the performance? Okay, how much efficiency we have improved? Okay, so that comparison with without fin can be expressed as fin effectiveness. So if the effectiveness is equal to 1 indicates that the addition of fins to the surface does not affect the heat transfer at all. So that is the heat conducted to the fin through the base area is equal to the heat transferred from the surface to the surrounding medium. The effectiveness is less than 1 indicates that the fin actually acts as an insulation, slowing down the heat transfer from the surface. So this situation occurs generally when fins are made up of low thermal conductivity material. So if the effectiveness is greater than 1, which indicates that the fins are enhancing the heat transfer from the surface. Okay, so here the use of fins cannot be justified unless the fin is sufficiently larger than 1. Wind surfaces are designed on the basis of maximizing the effectiveness for the specified cost or minimizing the cost for desired effectiveness. Okay. So mathematically here, the fin efficiency and fin effectiveness are related to the performance of the fin, but they are different quantities. Here each are related to each other like this. Then these are the problems for different fins. Here the circular uniform fin we have taken. Okay, and whose dimensions are given and temperatures are given, then film coefficient given, determine the temperature at the mid of the fin, efficiency, heat transfer rate from the fin, effectiveness. Okay, so first of all, while solving this particular problem, identify type of fin and its boundary conditions. So as per the boundary conditions, appropriately the heat transfer relations you have to select from the data book. Okay. Now for this particular case, the short fin with end insulated, we have assumed. So Q can be written as, for this particular case, HP Ka TB minus T infinity tan HML. M is equal to square root of HP by Ka. Substituting those values, we will get T is equal to 80.97 degrees Celsius. Okay. Similarly, take the another example. This is a motor body which is attached to a fin of a rectangular cross section. We have to determine the number of fins required. Okay, so this is the solution. Okay, next another fin we have taken. So with this I am closing the fins. Thank you.